Yeah, hello everyone. It's our pleasure to have Matthias here to share about his work. And today he's going to share about one interesting topics of how do you kind of do classical verifications of quantum learnings that you only have access to kind of untrusted like cloud quantum computing, for example. I think this is kind of very important topics because as we can see now, there are only couples of hardware providers in the world now, and then we do need to have this kind of proof of principle or even rigorous kind of proof that we can do some efficient verifications while ensure quantum advantage that when we utilize these kind of devices. Maybe Matthias can tell us more about it, and Matthias, the floor is yours.
Thank you very much. Thanks a lot for the introduction. And thank you also for inviting me and giving me the opportunity to speak here. So I'm Matthias. I'm currently a postdoc at Caltech and FU Berlin. And I'll tell you about classical verification of quantum learning, which is based on an archive preprint that we posted recently. And when I say we, this is a good opportunity to tell you about my collaborators. So this is work that I did with Marcel, Marius, Alex, and Ryan. The first three are at FU Berlin as well. And Ryan is currently at IBM. What am I going to tell you about today? So the motivation comes from a classical paper that has fascinated me by Shafi Goldwasser's group about verifying classical machine learning. So here, the motivation is roughly as follows. This is me. I have a laptop and I have access to the internet. And my laptop is not that powerful. And while the internet does contain some useful information, it's not exactly only high quality data. Now, if I want to solve a difficult machine learning task, I will probably have to address that. For example, I won't be able to train ChatGPT on my laptop. So what I should do is find some provider that also solves some machine learning problems, so also has access to data, but hopefully they have access to higher quality data and they can run more powerful learning procedures. Now, the problem is maybe I don't trust them. I might have to pay them to provide their service, but maybe I don't trust them. So the question is, how can I make use of their services and still be sure that the machine learning task gets solved and that in the end, I've learned a proper mapping from the input to the label? So this is the question of verifying classical machine learning, which is similar in spirit to verifying computation, but it has this added aspect of the difference between my kind of data access and the data access that the prover has. And maybe this is a good point to say. I will refer to this guy here as a verifier, and I think of that as a weak person or a weak computer. And the other player will be a so-called prover, which is somebody strong, but maybe not trustful. So this is the nomenclature taken from interactive proofs. This is the classical scenario, and we argue that if you think about quantum learning, something like this becomes even more important. So if you think about still me with my laptop and my bad classical data access, I might want to make use of quantum machine learning capabilities, but I don't have a quantum computer. And I also maybe don't have quantum data access, but I don't know, Google has, IBM has, Microsoft has, and maybe I want to make use of their services for machine learning. And this is what I want to tell you about today, about a rigorous result that guarantees that something like this is actually possible. More precisely, for this talk, we're going to look at this guiding question. What we want to do is we want to find a learning problem that has two features. The first is it should be intractable for classical learners, but efficiently solvable by quantum learners. And the second feature is that we want a classical verifier to be able to efficiently and verifiably delegate this learning problem to an untrusted quantum prover. Okay, so we want a problem that as a classical verifier, I cannot solve on my own. But if I have access to a powerful quantum machine learning architecture, but I don't have direct access, I only have remote access, then I want to be able to delegate my learning problem there. And this is what we're going to do in this talk. And in the end, I'll hopefully convince you that we have such a problem, showing that quantum machine learning advantages can be reliably accessed through delegation. The way I want to get there is I first want to tell you a bit about quantum computational learning theory, which is the framework that I'm going to use for the talk. And then I'll tell you about a new quantum data oracle that we had to introduce to make things work. With this, I can then tell you about the interactive verification procedure. And if we have time, I can tell you a little bit more about the oracle. So I'll start with an intro to quantum computational learning theory. And maybe this is a good point to say, if you have questions along the way, please feel free to interrupt me. I'd prefer for you to follow me for as far as I get during the talk. If I have to cut something in the end, it's not that bad. So how can we learn classical hypotheses from quantum data? To talk about quantum learning theory, we first have to talk a little bit about classical learning theory. And here, I'll just tell you the way we formulated it in this paper. There's many formulations, but this is the one we chose. So we look at something called alpha agnostic learning. And here the alpha is just a number. And alpha agnostic learning has the following ingredients. So the first thing is you have a benchmark class. So this is a class of models that you essentially want to beat, or at least you want to be almost as good as you could be with those models. So for example, this may be some classical neural network architecture that you want to beat, or something like this. Now, the way you want to beat them is using a model class. So the model class tells you what your machine learning model can actually output. Again, this could be some neural network architecture, some kernel model, something like that. Next, we make an assumption that there is some distribution class over n-bit inputs and 1-bit output. So this is because we're going to do this in like computational learning theory. We often focus on learning functions from n-bit strings to a single-bit string. And we're going to make some assumptions about the possible data distributions that can arise. And the final thing we need is an oracle. An oracle is a fancy word for how you have access to the data. And this could be, for example, you just get samples from the data. You could also have more powerful access. Maybe you can actually query the unknown function on an input of your choice. But either way, you have to specify your data access, or as a computer scientist would say, you have to specify your oracle. And with this, I can now write down the definition. So we call an algorithm A an alpha agnostic learner for the benchmark class B via the model class M with respect to the distribution class D from oracle access to O, if the following holds. So no matter what distribution from the distribution class we take, if we give the algorithm oracle access to that distribution, and we give it an accuracy and a confidence parameter, then with success probability at least 1 minus delta, the learning algorithm will output a model from the model class such that the following holds. The probability that if I draw a new pair from the distribution, that my model predicts something different on the input than the actual output is that I sampled. So this misclassification probability is at most epsilon more than the optimal misclassification probability that I could have achieved in the benchmark class. Okay, I know that this definition is a lot to digest, and I also realized I have a typo here, so let me insert it. I'm missing a prefactor that explains the alpha. So let me fix it. There we go. So let me go through this definition again. So we have this benchmark class, and we want to perform well relative to the benchmark class. So the goal is that after learning, the learner gives out a model whose error probability is only epsilon more than the best possible error probability that we could have achieved in the benchmark class. And we have this prefactor alpha that ideally we want to be 1. Not for all our results are we able to achieve this, but this is the motivation behind the definition. Okay. I hope this definition makes sense. If you have questions about it, please ask now. Otherwise, I'll continue.
Yeah, I have a question here.
Yeah.
So for like why you want to separate the benchmark and model class, could there be the same the same kind of like hypothesis class for it?
That's a good point. So oftentimes the benchmark class and the model class, you want them to be the same. So for example, you want to learn parities with parities or something like this. We separated them here for generality and because actually in one of our results we need that. But yeah, if you want, then for convenience, you can think about the model class and the benchmark class being the same.
Okay, yeah, thanks.
All right, then I'll go on. So this is the definition. Now, how do you get something like this? How do you learn? And in particular, we don't just care about learning in any way. We want to learn efficiently. And what I mean by this is the number of calls to the oracle and also the computation time that you use should scale polynomially in the relevant resources. So polynomially in the number of bits, in 1 over the accuracy, and in 1 over the confidence. And actually, the confidence will probably not appear anymore for the rest of this talk. I'll just fix delta to be like 0.01 or something. But in principle, delta is there in all the results. So for this talk, I'll make some simplifications. First off, we'll focus on a specific kind of oracle called example oracle. So this is what you might have seen before, where you just get like IID data from the underlying distribution. We're also going to assume that these distributions have a uniform input marginal. So remember, those distributions were over n-bit strings for the inputs and 1 bit for the output. And we're just going to assume that the inputs are uniformly random n-bit strings. That makes things a bit easier. And then finally, in my speaking, I'll make a distinction between functional agnostic learning and distributional agnostic learning. So here, functional simply means there is a function that describes the data. So in formulas, for any distribution in the class, we can actually write it as the input marginal and then some deterministic function that maps n-bit strings to a single bit. So notice that this means if I give you the input, the label is determined, and you have to figure out what the correct label is. And in particular, this is called realizable if we know that this deterministic function is always in the model class, in the benchmark class. In general, however, this need not be the case. So in general, it could be the case that even if you know the input, there's still some randomness in the label. For example, this could come from noise, or there may just not be an underlying function. So this is going to be some of the nomenclature that I use. Now, okay, how do you learn? One approach to this is using Fourier analysis. So you're probably very familiar with Fourier analysis based on sines and cosines. There's also Fourier analysis for Boolean functions. And here, if we have a function that maps n bits to real numbers, we define its Fourier transform as follows. We take the expectation value over uniformly random inputs, and then we take the expectation of the function phi of x multiplied with -1 to the s dot x. So these -1 to the s dot x, you can also view those as functions, and they form essentially the orthonormal basis that we need for the Fourier analysis in this case. So this is the mathematical formula, but if you want to have a simpler way of thinking about it, it's really the Boolean analog of Fourier expansion with sines and cosines, only that here we only have finite domain. Okay, how does this connect to learning at all? And here there is one very nice relation. So if we start from a distribution D that has uniformly random inputs and where the label may now not be deterministic. So it's like this phi is the expectation of the label given the input. So for example, this is just the probability that your label is 1 if the input is z. And this could be any number between 0 and 1. So if I give you such a distribution and I give you a function that maps n bits to a single bit, and now for convenience, we're going to relabel. So instead of mapping to 0, 1, we're mapping to 1 minus 1. The easiest way to achieve this is to take -1 to the power of the function. If you're dealing with 0, 1 valued functions, this is the same as taking 1 minus twice the function. And we're doing the same for this phi here. So I'm going to use the different phi symbol for 1 minus 2 phi. If you do all of this, then you can rewrite the probability that your function f misclassifies if you draw a sample from D. And you can rewrite it as 1 minus the inner product between the Fourier coefficients of, well, the relabeled function and the relabeled expectation phi divided by 2. So what this means is if the Fourier spectra are well aligned, then the misclassification probability is low. In other words, if you want to achieve a small misclassification probability, a good strategy is to learn the Fourier spectrum of this phi and then to try to approximate it to align with it well. And this is kind of the motivation behind a lot of Fourier-based learning approaches. And I want to show you just some examples. So how can these Fourier-based ideas help in classical learning theory? A pretty famous one is for functions whose Fourier spectrum has like a low degree concentration. There's an algorithm by Linal, Mansour, and Nissan from the 90s, and a recent improvement in Stock 2022. And then if you allow for a slightly different access model, so if you allow for queries, then you can learn Fourier-sparse functions such as disjunctive normal forms or decision trees. You can learn parities, and you can at least two agnostically learn Fourier-sparse functions, which is actually a result that we weren't able to identify in the literature, but that we kind of reprove as part of our work. So short summary, this Fourier perspective helps you learning a lot of relevant function classes.
Sorry, I have a question over here. So
Yep.
over here you consider like alpha agnostic, right? So for the alpha, yep, the larger the alpha, the easiest the learning will be, right? Is it?
Exactly right. So the larger alpha, the easier learning. So what we want is alpha to equal 1. And if I, for example, just write agnostic, then I implicitly mean one agnostic. And that's kind of the holy grail in agnostic learning.
Okay, I see.
Okay. So much for the classical part. Now let's actually do something quantum. So how can we get quantum computing into this? And one way of doing this is to work with quantum data. So instead of assuming IID examples, what we now assume are copies of a quantum state. And this quantum state is a so-called superposition example. So what it does is it's a superposition over computational basis state where the weights in the superposition are square roots of the associated probabilities. So in a sense, we just take the classical probability distribution and make it into a superposition. And this idea goes back to Chouty and Jackson from the late 90s. And now the setting is that you don't know this distribution. So your goal is to learn a function that kind of reasonably well aligns with this unknown distribution. And the way for you to do this is to try to measure copies of the state, to process the measurement outcomes that you got, and to then output a hypothesis that hopefully does the job. But the point is that we change the resource from classical examples to quantum superposition examples. And then we ask, is that resource more powerful than what we started with? Now, we know some answers to this, and these answers are typically based on quantum Fourier sampling. So quantum Fourier sampling helps us a lot. For example, it helps us with learning parities, it helps us with learning DNFs, and it helps us with learning Fourier-sparse functions. I want to highlight that these three are all examples where classically we don't know how to do it from random examples. We only know how to do it from membership queries, which is a stronger access model. So in this sense, it seems that these quantum superposition examples can do something that classical training examples cannot. But now notice that here I did not write psi d for a general distribution d. Rather, I wrote psi, and then I had a uniform input marginal and a deterministic function f. Then we know how to do this. Now, if you have a general distribution here, that's maybe something different than a deterministic function applied to uniformly random inputs, then we actually don't know what to do. There are some cases with noise where we do, but essentially we don't know how to generalize quantum Fourier sampling beyond the functional agnostic case. And this, in my opinion, is a big gap in our understanding of what these quantum data examples can do. Because the agnostic scenario basically says, I don't know exactly what the data is. So I don't know for sure that my model class can perfectly match the data, but I try to do the best with the model I have. This is, I would say, a pragmatic view on learning, and it would be good if we could incorporate that into quantum learning. So far, we don't know how to do that. Okay, now, what's our way around this? So our suggested way around this is to modify what we call quantum data. So we introduce a new way of talking about quantum data that is good for distributional agnostic learning. So concretely, we propose something that we call mixture-of-superpositions example. And here's in a comic how it works. So suppose the quantum learner asks for one quantum example. Then what's going to happen in the oracle that provides the example is the following. So first, the oracle decides on a random function according to a certain probability distribution over functions that depends on this unknown distribution D. And then once it has decided on that function, it's going to prepare the corresponding superposition state and send it to the learner. So what's happening here is we have lots of randomness in this unknown distribution D, and we're proposing to kind of pull it apart. So one part of the randomness we actually treat as classical randomness by picking a classical function. The other part of the randomness is, however, inside the superposition. So this is treated quantumly. And this is the new notion of quantum example we propose. In fact, this is similar to some examples that have, or some oracle models that have recently been considered in quantum complexity theory, where they're sometimes called non-standard or mixture quantum oracles. And this is a different way of approaching this idea now in the context of learning theory. Okay, so this is the comic. Let me actually also give you the mathematical expression. So what we say is that a mixture of superpositions example is a copy of this quantum state where we take an expectation value over a function drawn from the distribution f subscript d, and then we take an expectation over the corresponding pure superposition states. And now I should tell you what this distribution f is. It's actually the only sensible distribution you can come up with. So remember, we had uniformly random inputs, and then we had corresponding labels. Now what we're going to do is, if we want to assign a probability to a function, we just check how probable the single labels are that it assigns to different inputs and multiply all of that. So here's the mathematical formula. To figure out how probable a function f tilde is, multiply for all possible inputs the probability that if you look at this specific input, the label that you get out equals the label that the function predicts. So essentially, we're just asking how probable is a certain label assignment according to this distribution D. And why is this a reasonable notion of quantum data? Let's do two quick sanity checks. So the first sanity check is, if we're in this functional agnostic case, where we know that pure superposition examples are good, so where we have a deterministic labeling function, this actually just reduces to the superposition examples we already know. So it reproduces a known quantum example type. And the second sanity check is, if you measure this state in the computational basis, then what you're doing is just you get one sample from this distribution D. So that means it's a quantum extension of the classical notion of training data. And in particular, anything you can do with classical training data, you can also do with these examples. So in that sense, we argue that this is a reasonable quantum version of classical training data. All right, now I've introduced a new notion. The question is why? And the motivation, remember, was this problem. We know how to do quantum Fourier sampling if there is a deterministic labeling function, but we don't know how to do it in the more general case. And this is exactly what we solve with this new quantum data oracle. So what we show is that if you're given a copy of the state, you perform Hadamard gates everywhere, and then you measure in the computational basis, then you get an n+1 bit string out. And it has the following properties. The last bit is going to be 0 or 1, both with probability a half. And now the interesting thing happens if you observe a 1 there. So if you condition on this last bit being 1, and you then look at the first n bits, then the probability for seeing a certain n-bit string there is inverse exponentially close to the square of the Fourier coefficient evaluated at that bit string. And remember, this phi was the conditional expectation hiding in this distribution D. So this here describes how you get from inputs to randomized labels. So this result shows that with this kind of quantum data, you can actually approximately sample from the Fourier spectrum, in the sense that you can sample from a distribution that's essentially the squares of the Fourier coefficients. And to the best of our knowledge, nobody has figured out how to do this with these more established superposition examples yet. All right. So why am I so excited about quantum Fourier sampling? The reason why I'm excited about it is that with that subroutine, we can approximate Fourier spectra. So what I mean by this is the following. So first of all, we're going to look at an accuracy that's not like ridiculously small. So it's not, as you see here, 2 to the minus n half minus 2. And now what we show is that if you have 1 over epsilon to the 4 copies of a mixture of superpositions example, then we can efficiently produce an estimate of the Fourier spectrum. So here this phi tilde satisfies on the one hand that it's epsilon close to the true Fourier spectrum in infinity norm. And on the other hand, it actually doesn't have too many non-zero entries. So this zero norm counts the number of non-zero entries, and there are only 1 over epsilon squared many. So it's a relatively succinct description of a good approximation to the unknown Fourier spectrum. And here, this assumption on epsilon, I'm just going to make this basically for the next few results without writing it. I would argue it's a reasonable assumption. If you're a computer scientist, you typically care about inverse polynomially small accuracies, and then you will have this property. All right.
Sorry, I have a question. Maybe I missed that in your introduction slide. So what is the kind of like things that you can do with like Boolean functions? Because over here you have some algorithm that allows you to kind of like learn the approximate, kind of like have learn some Fourier approximations, right? And then so now you want to use this to do something, I think. So what would this be useful for? Yeah,
that's right. So the Fourier spectrum, the Fourier spectrum approximation is going to help us in learning Boolean functions. That's exactly right.
Yeah.
And we kind of take Boolean functions as a proof of principle playground to argue about the power of quantum examples in learning. So it's not necessarily about a direct machine learning application and image classification yet. It's more a proof of principle result. And I'm going to show you after this one, I'm going to show you 2 ways that you can use this Fourier approximation for learning Boolean functions.
All right. Okay.
So before I show you the application, let me just sketch the proof because it's actually pretty simple. So what we had before is we can sample from a distribution that's super close to the squares of the Fourier coefficients up to an error that's smaller than something like epsilon squared over 16. And on the other hand, there's a beautiful theorem by Dvoretsky, Kliefer, and Wolfowitz from the 50s, and a discrete version of it, which was observed a little bit later, for example, in this textbook by Kosorok. And that says if you want to approximate a discrete probability distribution to a certain accuracy tau, then you only need order 1 over tau squared samples from that distribution. Notice that this is independent of the support size of the distribution, which is good for us because the support size is exponential in n, so we don't want to depend on that. And now we can just combine the two, so essentially use dkw with an accuracy that's epsilon squared. We need the squares because here we have a square. And then you combine that with this approximate sampling, and you can get to a result. So long story short, we can do approximate Fourier spectra. And you ask, why do we do this? That's a very good point. So why quantum Fourier approximation? So one application of this is you can learn parities now using these mixture of superposition examples, and you can do it in a fully agnostic setting. So what we show is that if you have on the order of 1 over epsilon to the 4th copies of a mixture of superposition example, you can produce a bit string or a parity such that the misclassification probability of that parity, so here this inner product is just an inner product of bit strings modulo 2. So this misclassification probability is at most the optimum misclassification probability you could achieve with any n bit string plus epsilon. So that means what we have achieved is one agnostic parity learning, and we've even achieved it with the model class being the same as the benchmark class, namely the n bit parities. And what I want to highlight here is that this task, if you give me classical examples, is pretty hard. In fact, it's believed to be computationally hard because it's at least as hard as a problem called learning parities with noise, which is commonly believed to be hard and even taken as a primitive for some crypto problems. So this shows that we can solve this problem quantumly. And what I haven't explicitly put in the theorem statement is that it's not just the number of copies that is efficient, but even the computation time is efficient. So I wrote efficiently, I didn't show it, but the classical and quantum computation time used by this algorithm are also efficient. And then we can do something similar for Fourier-sparse functions. I'll skip over this for now, because I think we might better get to the verification stuff. So takeaway message from this slide is we have a learning problem, namely agnostic parity learning, that we believe is very hard to solve from classical data, but we can solve it using our quantum data, and we can solve it efficiently. Now, the question is, if I'm a classical learner and I would like to solve this problem, how can I make sure that I can ask a quantum person whom I don't trust to solve it for me? And this is what we're wondering about in the next topic, which is this interactive classical verification. So all up to this point was to build up a candidate learning problem. And now we're going to study that learning problem actually in verification. So a reminder, the motivation, if you're a capitalist, is you have a client and you want to outsource work to a server. Probably you have to pay a subscription fee for using that service. And the client maybe has a weak kind of access. So it could be like this classical example access, whereas the server has quantum computation and quantum data access. And then the goal is that the client can interact with the server in such a way that at the end, the client has a good hypothesis. Now, this is, of course, still informal. In a few slides, I'll show you what I mean by this rigorously. Before that, let me give some space to my inner mathematician and tell you about two assumptions that we have to make. So the first assumption is we have to assume that the unknown distribution has no small non-zero Fourier coefficients. Okay, what do I mean by this? I mean that this conditional expectation phi and its relabeled version, remember this was just 1 minus 2 this phi. If the Fourier coefficient is non-zero, then the Fourier coefficient is at least theta in weight. This is a technical assumption that we need for our proofs. And another technical assumption is we need a L2 bounded bias. So here we want the expectation of the square of this conditional expectation to be in some interval a squared b squared. I'm showing these assumptions because I want to be transparent about them. But fortunately, these assumptions, if you pick theta a and b suitably, are satisfied if the unknown distribution is, for example, known to correspond to a noisy parity or a noisy Fourier-sparse function. And that's enough for our purposes in regards to the guiding question, because classical agnostic learning is hard in these noisy settings. So even with these assumptions, we're still tackling tasks that are classically hard, and we're trying to verify them by interacting with the quantum prover. But I just wanted to show you the assumptions. So what are we actually doing? Essentially, you can boil down our procedures to an interactive verification of Fourier spectrum approximation. So what happens here is this following central ingredient. We've seen before, quantum Fourier sampling leads to quantum Fourier spectrum approximation, and this is crucial. So can we verify this specific subroutine of quantum learning? And now I'm afraid I'm going to need a whole slide to state the theorem, but take this also as a definition, because I'm going to explain to you while stating the theorem what I mean by interactive verification and what the kind of requirements are here. Let me start with some assumptions. So this theta must not be exponentially small, epsilon must be bigger than 2 squared b squared minus a squared. And we assume that the unknown distribution has this no small non-zero Fourier coefficients and the bounded L2 bias properties. Technical assumptions out of the way, now I can tell you about the result. So what we show is that there exists a pair of a classical verifier V and a quantum prover P that achieves the following. So first off, the prover is efficient. So this quantum prover uses a number of mixture of superposition examples that is efficient in everything. Theta, it's efficient in theta and even independent of n and epsilon. And it has also efficient quantum and classical computation time. So that's good. Prover is efficient. The verifier also is efficient. So in particular, you see an n-independent sample complexity and a good computational complexity. So this is the first ingredient we need for a reasonable interactive verification strategy, right? So if I want to outsource my learning problem, the party that I outsource it to must be able to efficiently solve the problem. Otherwise, I'm never going to get an answer. And I myself have to be able to efficiently verify. Otherwise, I'm not going to be done in time to use the model. And then we have two more properties. The first is what a complexity theorist would call completeness property. So what we say here is if the verifier interacts with the honest prover P, then the verifier is going to output a good approximation to the unknown Fourier spectrum. So it's going to output a phi tilde that is close to the unknown Fourier spectrum in one norm. And it's again, it doesn't have too many non-zero entries. And this happens with high success probability. So if the prover actually does what they're supposed to do, then in the end, the verifier has a good Fourier spectrum approximation. And the counterpart to this is a soundness assumption. So what if the prover tries to cheat? And here we show that we give a protocol such that no matter what the prover does, so the prover could cheat, the prover could just be incompetent, and the prover can be arbitrarily powerful in trying to fool the verifier. No matter what the prover does, the probability that the verifier accepts and outputs a bad approximation is very small. So only with very small probability will the verifier interact with a dishonest prover and still accept and output something wrong. So these are also the central ingredients for all our verifications. So we define this interactive verification by saying the honest prover should be efficient, the verifier should be efficient. We have a completeness property, so when interacting with an honest prover, things work. And we have a soundness guarantee saying no matter what the prover does, things can't go spectacularly wrong. All right. It took me a while to state the theorem. The proof is going to be a bit shorter because I'm skipping details. I'm just going to show you essentially how the protocol works. I'm not going to prove that it works. For that, I have to point you to the paper. So the protocol works as follows. First, the verifier asks the prover to send a list of all non-zero Fourier coefficients of the unknown function. And now what the prover does, well, the prover is a quantum prover, and it has this quantum data. So we've seen that the prover can use that quantum data to approximate the Fourier spectrum. So they just do that. If the verifier could trust the prover, then you could stop here. Now the verifier has an approximation, they can just work with it, and they're happy. But if the verifier cannot trust the prover, we need like a backup step, right? We need the verifier to check what the prover does. And essentially the verifier proceeds as follows. So first, the verifier uses their own classical data to estimate the Fourier coefficients that P sent. So the verifier is not going to trust what the prover sent. It's going to like produce its own estimates for those coefficients. And then verifier checks whether the total accumulated Fourier weight is large enough. And then the verifier is happy. But if this is not the case, so if there is so much Fourier weight missing that the prover could be hiding an important Fourier coefficient, then the verifier is going to reject the interaction. So these last two steps are kind of the fail-safe that we've built in. And our assumptions are such that you can actually prove that this protocol works. So the verifier asks the prover for some information, the prover sends it, and the verifier double checks. And only if the information seems reasonable, then the verifier is going to accept it. So this was Fourier spectrum approximation. Now let me just show you one application of this in learning. So we can get a similar result for agnostic parity learning. So here, the same preamble as before. And what we show is, again, an efficient quantum prover, an efficient classical verifier. And this time, if the verifier interacts with the honest prover, then it's going to output a parity like we wanted in the agnostic learning guarantee. So the probability of misclassification with the output is at most the optimal misclassification probability plus epsilon with a high success probability. So that's the completeness. And the soundness is, as you expect, no matter what the prover does, the probability that the verifier outputs something that violates the agnostic learning guarantee is low. And you can essentially get this as a corollary from the Fourier spectrum approximation. I'm not going to show the details here. But this is also how you can define interactive verification of learning. So you want the prover to be efficient, the verifier to be efficient. If the prover does the right thing, you want the verifier to produce an output that satisfies the agnostic learning guarantee. And no matter what the prover does, the probability of getting an output that fails to satisfy the guarantee should be small. And importantly, this shows that the verifier here solves a problem that they could not have solved on their own. Because classically, one agnostic parity learning is hard. So rather what they do is they outsource work to the quantum prover, and then together they can actually solve the problem, even if the verifier does not trust the prover. Okay, and okay, you can do the same for Fourier-sparse functions. I think I'm again going to skip it just for time reasons. Do you have any questions maybe about the statement of the theorem, what this means from a verification perspective?
For me, I think that the theorem looks fine for me, but I do have questions.
Yeah, please.
Is that how do you kind of like mathematically kind of like laid out the details of the action of the dishonor verifiers? Sorry, dishonor prover.
So you don't model the dishonest prover at all, essentially, because the dishonest prover could be absurdly powerful, and you don't really know how to model it. Basically, you have to design your verifier protocol in such a way that it only depends on certain properties of the output that it got. So, for example, here in our proof sketch, the verifier works with the output that they got from P. And essentially what you have to show is that if the list of coefficients that P sent is bad, then V is going to notice this, independently of how P produced the bad list. And this way you can kind of get around dealing with infinitely powerful adversarial provers.
Right. Okay. So basically, if I want to, for example, apply your protocol to some other task, for example, then I have to first like think about one task that's like hard for classical but efficient for quantum, and then I have to kind of like find a kind of verifier protocol in order to kind of deal with the dishonor approval, and then have to kind of design some algorithms or protocol based on the problem that I choose. That over here you have like the Fourier spectrum of like learning stuff like that.
Yeah,
and then it's basically all going together. Okay, sure.
So the way we've set it up, you can essentially deal with any learning problem that requires a Fourier spectrum approximation. But this is kind of specific to this whole Boolean learning theory framework. So if you care about other kind of learning problems, you're going to have to change this. That's right.
Right. But then the kind of step, the proof ideas all are the same. Now you have to be clever on how you design the verifier protocol, like 0.3 and 4. How do you do the rejects if you kind of get some weird result from the approval?
Exactly.
Okay. Cool.
All right. Yeah, so as I said, I'm going to skip the Fourier-sparse thing. I want to say one last thing about our results. Namely, in a sense, they're close to optimal in a certain degree. So I had this weird assumption that epsilon is bigger than 2 times square root b squared minus a squared. That's a bit annoying, right? Because epsilon is the accuracy we can achieve, and I'm saying it has to be larger than something. So I'm putting a lower limit on how accurate we can be. That actually seems bad. And we were also a bit worried about this, so we looked into it in a bit more detail. And what we can show is that you can't do much better. So we show that if you want the same kind of interactive verification, you cannot at the same time achieve 2 things. The first thing would be you improve this epsilon lower bound to even just a third times square root b squared minus a squared. If you at the same time want the verifier to have a sample complexity that's independent of the number of bits in the input string, you cannot get those 2 simultaneously. It's just not going to work. So that means to a certain degree, our results are optimal because improving this accuracy limitation would significantly worsen the sample complexity of the verifier. And here I want to give you a proof sketch because I really like this idea. And this is actually not originally our idea. This is inspired by a paper by Matthias and Schaffer that appeared in Calt. So roughly, the idea is the following. You take the classical quantum pair of verifier and prover. You use that to build a classical distinguisher between random noisy parities and the fully uniform distribution. And then you say, well, we know that this distinguishing problem cannot be solved with fewer than omega of n samples. And then you have a proof by contradiction that you cannot at the same time have the classical verifier with sublinear sample complexity and this known lower bound. And the reason why I find this proof so pretty is the construction of the distinguisher from the verifier approval pair, because I think this is quite powerful. And roughly it works as follows. So the distinguisher gets access to samples from a distribution D, and this D is either a noisy parity or fully uniform, and it has to figure out which of the two. Now, what the distinguisher does is it basically feeds those samples to the verifier, and now it's going to simulate a verifier-prover interaction where the prover has access to a mixture of superpositions quantum oracle, but with a specific distribution, namely the fully uniform distribution. So note that this is essentially a useless oracle, because the fully uniform distribution doesn't carry any information. It's like a maximally mixed state, essentially. So in particular, you don't need any quantum data to simulate this. You might need a quantum computer to simulate P. If you're a classical person, that might require exponential resources. But since we focus on sample complexities here, that's fine. From the sample complexity perspective, this is going to be efficient. So now you simulate the interaction of the verifier and the prover, and you only have to add one more step, which is if the verifier outputs a hypothesis, you have to check what the performance of that hypothesis is using a few more samples. And if the hypothesis performs well, or if there wasn't a hypothesis to begin with, you say, okay, that must have been a noisy parity. If the hypothesis performs badly, you say it's uniformly random. And the idea here is that the verifier gets access to D. Now, if D is the same as the fully uniform distribution, then basically by completeness, the hypothesis output by the verifier is going to perform like, okay, as best as it can, but with respect to a fully uniform distribution. And you cannot perform well with respect to complete uniform randomness. So you're going to perform badly and end here. In contrast, if this is a noisy parity, then the prover actually has the wrong oracle. So that's the same, that's effectively a dishonest prover. And you can use the soundness guarantee to say that the verifier either will reject, or should it not reject, by soundness, it's still going to output something that performs well. So this is the general idea for getting a distinguisher from an interactive verifier approval pair. And while this reduction here was not computationally efficient, it's sample efficient and proves that our result cannot be much improved. All right. I could go into more details about the limitations of our quantum oracle, but I want to leave time for questions. So let me just say the following. I've introduced a new kind of quantum data oracle, right? These mixture of superpositions examples. Now, if I introduce something, I should be careful to not introduce something trivial. So either it could be trivially useless, that would be bad, but I've already shown you that it can do things, so it's not useless. It could also be trivially all-powerful, and that would also be bad. So to show that this is not the case, we prove some limitations. And in particular, we prove a limitation that it shares with their standard superposition counterpart, namely that if you go to so-called distribution-independent agnostic learning, you don't really gain anything over classical data. And in fact, we can show something similar also for verifying in a distribution-independent setting, which is this result, basically adapting a similar reasoning from the classical case. Okay, so sorry that I rushed through this a bit, but basically the message I want to convey is the kind of quantum data we defined is not trivially all-powerful, it has its limitations. So you have to really look at what kind of machine learning tasks it's good for. All right, let me conclude, and then we have time for some questions. So the first thing I told you about is we proposed this mixture of superpositions quantum data oracle, and we showed that it's very powerful for agnostic learning if you know that the inputs are uniformly random, but we also showed it's not arbitrarily powerful. And in fact, we showed a little bit more than this. So in the paper, you will find this table that gives you a bit of an overview of our results. I did not mention all of these in the talk. So for example, we look at a different kind of quantum data access called quantum statistical queries. But if you're interested, you can find these results in the paper. And then we used this to identify learning problems that at the same time are believed to be classically hard, but that a classical verifier can efficiently solve when it interacts with a quantum prover. And importantly, it doesn't have to trust that quantum prover to make use of the quantum power. Let me add one thing. It's kind of important here that I was banging on about agnostic learning. It turns out if you don't have agnostic learning but realizable learning, verification becomes kind of trivial, even classically. So that's why we invested all of this work in understanding agnostic quantum learning algorithms. And that's also why we even though our goal was verification, we first had to understand agnostic learning better. So these were the results that I told you about. Now, where could you go from here? I think one interesting open question is to actually understand whether our mixture of superpositions examples are needed. Because I did not claim that superposition examples cannot do agnostic learning. The only thing I'm claiming is so far we don't know how to do it. And it would be interesting to either see whether they also are a suitable resource for agnostic learning, or maybe there's a provable separation between superposition examples and the mixture of superposition examples that we introduced. This, however, would still be in computational learning theory. Now, you should view these results as a proof of principle result. There are learning problems where a classical learner alone cannot succeed, but they can outsource them to a quantum prover and then they can succeed. I believe that this will be very interesting to study in other scenarios. So for example, there's been a lot of work on distribution learning with quantum models. And recently there's been lots of interest in learning with versus without a quantum memory. And I believe that asking about verification in these scenarios will also be fruitful. And in fact, we're currently working on this learning with versus without quantum memory direction. And then finally, and maybe the setting that you're most familiar with, is variational quantum machine learning. So one reason why quantum machine learning is so popular these days is that we think it might be NISQ-friendly through these hybrid algorithms where the quantum architecture does part of the work, and then you have a classical optimizer. So one question would be, can you make our framework NISQ-friendly and say something about variational quantum machine learning models? Or you can actually ask a different question. So you could ask, say, maybe at some point we're gonna have fault-tolerant quantum machine learning, but not everybody has it. Maybe more people have NISQ quantum machine learning architectures. And then you can ask, are NISQ devices powerful enough to verify fault-tolerant quantum machine learning? And I believe this is another direction where we don't say anything about this in our work, but I think it would be interesting for follow-up work. All right. So thank you very much for listening to me for so long. And now, if you have any questions, please go ahead. I'm happy to answer to the best of my ability.
Yeah, thanks, Matthias, for the very concise overview of your work. Yeah, now I kind of like understand more on the kind of like the steps as well as the sketch of your kind of theorems. So for the audience, if you have any question, you can unmute yourself to ask the questions, or type it in the chat, then I could ask a question for you. Maybe I could start off with a question for me. Over here, you just please assume you have kind of, you can interact with like one distrust like prover, right? Yeah. Like what if like we'll kind of like assess the interaction with the second like prover, like dishonor prover makes the kind of like verification step easiest, or will it make it harder?
Yeah. I think that's a very cool question, and it's something that I don't know enough about. So what you're hinting at is something that people looked at in complexity theory. So in complexity theory, it can sometimes help to have multiple provers. Roughly, so it's often explained with the motivation of this prisoner's dilemma in mind. So if you kind of have two gangsters in prison, but they're not allowed to talk to each other. You kind of question them separately and you compare the answers they give, and that can give you more information than just questioning one of them. And similarly, you're right that if you have two provers, that could actually be more helpful than one prover. I don't know the answer to your question, but I think it would be interesting to study whether this is the case in learning theory. But yeah, I don't know, unfortunately.
Yeah, because like I think your work kind of serve as first step to go into this direction, because eventually, like in the future, we have like different providers of like quantum hardware, and we can utilize those hardware to basically cross verify each other's. And
Exactly. Yeah, I think that's a cool idea. Like, I don't know if you trust neither Google nor IBM, maybe you can pay subscription services for both Google and IBM, and then in the end you can trust both of them because you verified them.
yeah, and the other question that I have, just wondering, because over here just assume that okay, you know beforehand that whether it's a trusted or like distrusted like prover, right? Like over, could you relax these assumptions and use your our protocol and trying to kind of distinguish whether it's trusted or distrusted approval?
Yeah, so for our protocol, we don't really assume anything about the prover, whether it's trusted or distrusted. It's only that you're right that the protocol kind of is asymmetric with respect to those things. So if the prover does what they're supposed to do, then things go well and we get a good output. If the prover doesn't do what it's supposed to do, then we're just not going to get anything useful. Like, let me maybe take this version. So there is an asymmetry here, but you're right that you could use this to detect dishonesty on the level of the prover. So in a sense, if you look at this step of the proof, this step 4, V is either happy or V rejects. And you can think of this V rejects as it tested the prover and it came to the conclusion that the prover either was dishonest or wasn't doing their job well enough. So you can view this as like testing whether a prover is honest. Yeah.
Yeah, I think this could be kind of interesting. And I think for your protocol is okay. So I couldn't tell, like, is your protocol hard to implement in real life? Because over here you have the proof of principle examples, right? And I think this protocol should be simple enough for people to use it to kind of like detect like dishonor,
Yeah.
prover or computer providers.
I agree that the protocol is simple. I think the main issue is the resource. So if you want to implement our protocol, you kind of need this quantum example. And this might be hard to get. So
Right.
typically, when people talk about how to get this pure superposition example, they talk about this needing a quantum RAM.
Okay.
Which is, let's say, at least hotly debated whether it's possible. And then we need even a little bit more with like this random function. So in that sense, it's a proof of principle in that this resource is not just like easily available. Right. And that's also why it would be interesting to, for example, go to variational quantum machine learning, because these are a bit closer to practice.
I see. Okay, I think maybe the time's up. Maybe we'll just don't like drag you any more further because it will be like 7:04 at your site. I think we can kind of like reload the seminars, and thanks again, Matthias, for the very interesting talk. I hope to see like more work in this direction in the futures, because yeah, this is exactly what we are lacking. And currently, we like for the like quantum learning research that we have, we just like assume that we have like we trust the quantum computers, and then yeah, it's better to have this kind of framework in order to have a more secure like in terms of like result complications. Yeah, thanks again, Matthias, for your talk, and see you like next time. I'm not too sure when it will be. Yeah.
Thank you very much, and thanks everybody for listening.
Yeah.